All right. Hello. Hello. Hi. I'm Vikraman. I'm at the University of Glasgow as a postdoc with Simon, and I'll tell you about some new ideas that I've been discussing with Simon about semantics of session types. And I should say that I'm an outsider to concurrency and session types. So I come from a background in type theory and category theory, like in the normal functional style. And so I've been trying to understand session types better using things that I know about. And so this talk is about things that are very much work in progress. And I'll tell you about some things that I think are important or important gaps in the theory of session types and how these could be fixed. And so let me start by so the title of this talk is Classical Processes in Modern Dress, and I picked up the title from a paper of Martin Hyland, which is Classical Lambda Calculus in Modern Dress. And it's a very nice expository paper which explains what, like at least in the last 30 years, what has happened in basic foundations of lambda calculus. And even though like we often think about just lambda as a binding operator, which hasn't changed much for a long time, there are many tools and frameworks for thinking about these kinds of type theories and binding operators. And so there's a lot of modern technology in functional programming, or at least in simply typed and dependently typed type theories. And it seems that so these questions are quite hard when you go to linear logic and linear lambda calculi, and in session types it's even harder. So I tried to not go into the state of the art in these techniques, but just show you a little bit of what these kinds of tools can give you. So can session types be done in these frameworks? And we've been exploring, but so far I don't know if it's going to go, and if there's some big thing that we are going to find out at the end. So let me just continue. Just to start, I want to give a bit of motivation about why would you want to think about foundations of programming in a different way. So generally, like if I were giving this talk as a programmer, and you asked me what is a program, and then I would just say it's a string of symbols and it's a bunch of instructions that you give to a computer, which is usually a machine. And then so what exactly is a computer? It's a physical device. It has some notion of computation. But as programming language theorists, we completely ignore all the physical notions and take an approximate notion, which is to say that there are programs, they're abstract syntax trees, and the notion of computation is just reduction of programs, right? And so, of course, there are many languages, and they have different abstract syntax, and programs may reduce, may or may not reduce, and they might keep reducing. And as the user of a program, you're looking to plug in an input and wait for an output, and you want some notion of normal form for these programs, right? So this view of programs is an approximation of this physical process, which we think of as computation, right? Okay. So the same thing could be said about processes, right? So what is a process? It's a program or some other metaphysical notion, which so in session types we care about message passing and programs interacting with programs, and so again these are physical notions. Okay, but when we go to type systems, right? So this, I think, so going back to John Reynolds, who used this terminology of the difference between Curry style and church style. So in extrinsic typing, you have programs like the untyped lambda calculus programs, and you realize that they're not all well behaved. And as a programmer, I want to say that my program should follow some specification, or it's a predicate on my programs. And this, so when we take that view of programs, so types are an afterthought. So I write my program first, and then I give it a type, and then as a PL theorist, when we design languages, we think about reductions and whether the program you started with has the same specification after reduction. Okay, and this is very well known that there are good notions of what types should be, and if you set up your typing rules and reductions correctly, you get some well-behaved notion of normal form. Okay, so that's a very old view, or I mean, I know that both of them exist right now, but so then there's the other view, which is intrinsic typing, which says that, okay, so there are no untyped terms because you shouldn't be able to write untyped terms, because the only programs which make sense are the ones which have types. And if you take that intrinsic view of typing, then terms are typed, reductions are typed, and every term, because it has a type, we should be able to ask whether it has a normal form. So the notion of normal form changes a little bit, but essentially it'll be something of the same type which doesn't reduce any further. Okay. So this is great, but we're still talking about reductions and programs with normal forms. So, but there's also the other point of view, which started, actually way before operational semantics was there, because the field of programming languages started with denotational semantics, and then the point of view was that programs are strings of text, but they are actually mathematical objects. And when you think about mathematical objects, you don't think about physical construction. So when I say what is a function, I don't have to say it's a lambda term. A function is a binary relation which is well defined in total. It's a basic axiom of ZFC from which I can define functions. So the primitive notion of programs as mathematical objects is, I think, the purest that you can say, like, okay, so programs have to be some sort of mathematical object, and when you write down programs that have a type, they classify some sort of mathematical structure. Okay, so this is sort of the intrinsic point of view, which is to say that every well-typed program you write is denoting some mathematical object, and that's where denotational semantics comes in. And to be able to say that, okay, my programming language exactly classifies all the let's say computable functions or functions which consume finite amount of memory. So these kinds of expressivity properties are things that type theories give you. Okay, and it's not just, so I mean, in this community we all know about Curry-Howard things. So another point of view is that, okay, when I'm writing a program, I'm performing a logical deduction in some system. So when I'm writing in this presentation of the simply typed lambda calculus, I'm actually writing a natural deduction proof, and so that's the Curry-Howard view. But they don't have to be just proofs. So there's the whole field of denotational semantics is to assign meaning to programs which are not proofs or programs, and mathematical objects outside this universe. So the simplest semantics for simply typed lambda calculus is that types are sets and programs are functions. So if I write a lambda term a to b, the meaning of this type a to b, it's exactly the set of functions from the meaning of a to the meaning of b. And so sets and functions are in some way the most primitive objects in programs or functional programming, and it's not just one model. There are many models of the lambda calculus, and there are recipes to generate these models, which is what this talk is about. If you go back to early domain theory, there's the whole denotational semantics of PCF using domains and continuous functions. I mentioned this weighted relations model because it comes from linear logic. So if you have a model of linear logic, you can build a model of the lambda calculus and things like that. So this is a different perspective on programming. And now, if I wanted to talk about the simply typed lambda calculus, the simplest thing to do would be to write a presentation of the simply typed lambda calculus. So usually, all these presentations more or less follow this schema where you have types and terms and equations or reductions, right? Okay, so I tried to write like a relatively good presentation of STLC. So you have types and you have judgments which tell you what the well-typed terms are, and judgments which tell you what the equations are. So when you write the terms, you say that gamma derives E1 of A, E2 of B, and then you can form pairs which have the product type and lambdas which have the function type. Okay, and then the things you care about are things like weakening and substitution. And once you have these good properties, you can write down an equational theory which has beta eta equations. So the beta equation is where computation sort of happens, where you substitute values for expressions and reduce one step. And then there are eta rules, which also can be seen as reductions and sometimes not. But so the lambda calculus, as presented like this, is okay. It's a huge thing to write, right? But there's a very simple way of saying what the STLC is, and these are facts that have been known since the 70s, like Lambek and Scott's categorical logic book. So STLC classifies the theory of lambda calculus classifies the theory of Cartesian closed categories. So now I'm going to use some category theory, but I'm not going to talk much about concrete categories or anything. I'll just vaguely tell you what Cartesian closed categories are. So Cartesian closed categories have objects and morphisms, and Cartesian closed means you add some more structure, which is just enough to interpret the lambda calculus. Okay, so you add the unit type 1 and times and functions, and the essential feature of a Cartesian closed category is this closure property, which is an adjunction which says exactly these three. So this is in logic where you say if you assume A and prove B, then you can prove the implication A implies B. This is like the deduction theorem from proof theory. Okay, and then if you are writing a term language, which is the lambda calculus, you write a lambda term for this function type. Okay, and if you are working in a Cartesian closed category, you just replace all of that with gamma times A, arrow B. So arrows are arrows in the category. So gamma times A is an object, B is an object, and the currying adjunction, it says that whenever you have this, and you can go from a program like that to a program like that, and the other way. So each of these rules are reversible, right? You can go from top to bottom or bottom to top. Okay. And so this correspondence that I'm saying, it's a correspondence in a very technical sense, as in so we know about the Curry-Howard correspondence, which is that if gamma derives A, then there should be a lambda term gamma derives E of type A, and if I have E of type A, I should be able to get a proof. And this correspondence extends to categories. So you have logic, you have programming, and you have programming languages or type theories, and you have categories. So what happens is, so you have propositions as types as objects, and proofs as programs as arrows. Okay, and so categories go even one more level higher, which is, so we normally stop with Curry-Howard at types and terms, but when we go to categories, we can talk about whether two arrows are equal. So when you say that two lambda terms are equal in the lambda calculus, which means up to the beta eta equations, you can show that they exactly show that the interpretation of these lambda terms as arrows are going to be equal in the category. Okay, and this is not just one way; it goes the other way. So if two arrows in this so you interpret two programs, and if they're equal in the category, then there must be an equation in the lambda calculus which will prove the fact that these two terms are equal. Okay, so this is very, very old, and it has been known for a very long time, and this is sort of the simplest Curry-Howard Lambek correspondence, because it is very crisp. Like so, if just to give you a taste of how much further this correspondence has changed, because using more modern tools, what we can say is that we have a presentation of the free Cartesian closed category on some set of base types. Okay, so any presentation of lambda calculus that you write is going to satisfy this property that whenever you have some Cartesian closed category which interprets the base types, there is a unique way to extend this to an interpretation of the lambda calculus in C. Okay, and so this interpretation it's not just a function on terms. It's a functor, which means it actually preserves equations. So when we do things like translations, we are actually when we are translating the lambda calculus into some other language preserving beta eta equations, we are actually constructing a CCC functor, and so this is a very fundamental property, and further, the lambda calculus has a very much more interesting completeness theorem, which says that if it's any Cartesian closed category, it could be sets or any other Cartesian closed category, as long as it's not degenerate, this interpretation will, if two terms are equal in the model, they will have to be equal in the language, and this goes back to like 1950s. Harvey Friedman's completeness properties, and these are more or less like a modern presentation of old ideas. Okay, so this is great, but what can you do with this? Well, there are many meta-theoretic properties of the lambda calculus that fall out of just this basic fact, and these facts have been, so if you had to show that lambda calculus has normal forms or strong normalization, you have to give it a reduction semantics and prove Church-Rosser by doing very complicated induction. But these tools give you a reduction-free way of proving important normalization results. Okay, and the fact is that the other fact is that sets and functions are, because it's Cartesian closed, it's a very fundamental structure for functional programming. Okay, so I wanted to say, so I've been talking about lambda calculus, but there are many other languages, and many people have been thinking about categorical semantics for their languages, and there's a very long list, and I wanted to just point out that people normally talk about lambda calculus, and then there's polymorphic lambda calculus, which has Lambek correspondence and Martin-Löf type theory and toposes. If you care about programming, so call by value lambda calculi, as Eugenio Moji showed that a strong monad can axiomatize it. I wanted to also mention S4 modal logic, which Frank Fenning worked on, and it also has an axiomatic semantics using monadal comonads. So where do session types come in? And that's the question I wish to explore. So all of these languages, like they sort of have a Cartesian flavor. The substructural rules don't change much. But when we go to linear logic and linear lambda calculus, the situation is much more complicated on the rightmost side. So if I took the linear lambda calculus, which I'm calling intuitionistic linear logic, so it's just with tensor and a lolly, and this can be shown to be in correspondence with symmetric monadal closed categories. Okay, and so I mean there are many variants of linear logic, and some of them have categorical semantics. So MLL, which is MLL without negation, it only has tensor and par, and there's an axiomatization in linearly distributive categories. And then there's linear nonlinear logic, which I think that DIL is a term model for LNL, and it should correspond to LNL models. And then classical linear logic by Curry-Howard has been shown to correspond to classical processes or hypersequent classical processes, and they should have something on the right. So So what is the right structure to capture session types? There was the famous the proofs as processes program by Abramsky, which people started thinking about it a lot, and so there is a lot of work by people, and everyone had a different opinion on what the right language for concurrency should be. So before session types were invented or were mainstream, I think. So people were trying to take the pi calculus and find a correspondence with linear logic, and so Bellin and Scott was one of the important ones, and I think so Abramsky and Simon and Nagarajan, they came up with interaction categories and specification structures, which are a term language for linear logic with the semantics, and sure. So and people have tried to find correspondence between proof nets and pi calculus, and the other very important work in the pi calculus was by Sangiorgi and Fiore, where they showed that if you take pi calculus and tweak the bisimulation relation, you can get a fully abstract model. So set to the I is a perfectly fine model for the pi calculus, and it's a completely mathematical model. Okay. And in session types, the Curry-Howard program started with Karj and Fenning, and then Wadler did it for classical processes, and CP has been extended by various other people, and I think the most recent one is by Wen Koka and others. People have also been thinking about denotational semantics for these systems, and I think one of the first papers was by Bob Atke on where he used a relational model to explain CP. Okay. So, and also Ryan Kavanagh's work and various others, which I tried to mention. Okay, so I'll just quickly, if you haven't seen CP, because it's a very, like a very simple calculus in which you never want to write programs, but it's just a term model for a presentation of linear logic. So you have different kinds of types for tensor and par and coproducts and products, and you have a duality relation on types. And then there's a judgment which says a process in context gamma is generated by these rules, and so the simplest rules are usually axiom and cut, which says you can create X, A, and A dual, and cut, which allows you to put two processes. Okay, so I think that should be A dual, not B. But so when two things are dual, you can put them next to each other. Okay, and then there's sending and receiving using tensor and par, and this is normally how the system is set up. So this is a presentation, and what does it mean in terms of categorical semantics? So more or less the key idea that after reading a lot of papers on session types and trying to understand what exactly is the common thing between each of these typing rules, more or less my intuition is that so in lambda calculus, functions are we create functions by lambda abstraction, but when you add duality, this function type splits into two things, and in fact, so you add a duality operation on types, which allows you to type things which are A and A dual, and okay, so I mean it's a string of symbols in categorical notation, but what it means is that these two junctions are very fundamental to session types, or I think so. So let me quick, if you want to know what exactly is the model, so this is sort of the model which I think works for most systems of session types. So you take a category which can interpret your tensor products and your pars, and then you add a duality involution which splits your types into two things. Okay, into two adjunctions which allow you to make these processes interact. And so what happens in CP? So I'll just show you, for example, two different rules. So you have a process in type gamma, and this exactly gives you an arrow from 1 to gamma. And so if gamma has x1, A1, x2, A2, it's interpreted as a tensor of all these things. And so each rule has an interpretation, and just from these few basic facts, you can build all the structure of CP. And it involves some algebraic manipulations using adjunctions, but the point is that finally you get a theorem which says if P is a well-typed process, then you get an arrow from 1 to gamma, and this is built up compositionally by combining the semantics of each type constructor and term constructor. And well, if you add choice and branching, and so that corresponds to coproducts and products. Okay, so the last few minutes I just want to say, so okay, this is great, but it stops at types and terms, and what about reductions? So it seems to me that there is, I think other people have mentioned as also that so there is a lack of a typed equational theory in CP. Okay, so in CP, there is even a worse problem, which is that the reductions are on configurations, not processes. And what would be a typed bisimulation or a typed or a judgmental presentation of what two processes being equal should be? Okay, so going from CP, so CP has a bunch of problems, and HCP comes and fixes it. So for example, CP requires you to put two processes next to each other as a term, but so in HCP, you don't have to do that because now you have this double binder which allows you to put to cut between X and Y in two different environments. So HCP has this notion of environments and hyperenvironments, and so CP can be improved, the presentation can be improved, and so it's not important how much the typing rules change, but the same kind of soundness theorem also holds for HCP. And now HCP has a notion of bisimulation. So the recipe for writing bisimulation in these session-typed languages is you just forget the types and go back to PyCalculus and use PyCalculus rules, right? So if you try to reconstruct these label transition systems using types, you notice that it's only the tau transitions that preserve types. And in fact, so the semantics that I showed you, it allows you to prove that if you have a tau transition and it's on some hyperenvironment G, then they produce equal arrows in G. Okay, so I don't know if this can be improved, but what about the non-tau transitions? I know there's some work in progress by some people. I'd love to know more about it. Okay, so just to summarize what all this means, so I'm claiming that there is a family of models for these languages, and any category where you can find this axiomatic structure is going to be a sound model for this language. So the simplest model is the category of sets and relations, and if you instantiate the semantics, you recover Bob-Atkins semantics. If you like geometry of interaction, so if you instantiate geometry of interaction on the category of CPOs, it becomes a compact closed category which also has this structure, and this recovers Ryan Kavanagh's domain semantics for CP. But both of these models are actually degenerate. They don't tell you much about what's actually concurrent. So there are better models where this structure exists, and so these are quite technical to explain, but maybe many of you might know about event structures. So there are many variations on event structures, and you can look at them as games. So if you take concurrent games and winning strategies, that also has this sort of structure. So this gives you an interpretation in event structures. Okay, and once you have a model, there are many different things you can do. So either you can extend, so you could ask the right questions about syntax, but by looking into the model. So for example, the fact that these two ends are different, well, it's a fact about star autonomous categories, like not all of them have to be the same. Or you could characterize process equivalence by looking in the model and trying to see which processes are equal and then trying to extend your syntax or equations to fit that notion of equivalence. Or you could just go to the model and say that two programs are equal if they're equal in the model. So for example, in event structures, if you have two processes interpreting event structures, they'll be equal if they have the same causal history. Okay? And there are many other things which could be interesting, like understanding deadlock freedom more semantically and understanding these translations and other extensions using, yeah. So I'll stop here, which, so this is the goal of the project, and we hit many problems, and I'd be interested in feedback or advice.
Okay,
thank you.
Let's take some time for questions.
Thank you. Can you repeat what you mean the problems of CP? When I mean in your undertaking, you identified like there are a few problems in CP. What are those problems exactly? Can you repeat?
Where are the problems?
Yeah.
Yeah.
You said something like reductions and
Yes.
configurations are not processes.
Right. So.
Something like that.
That's.
Right.
Yeah, so in CP, the reductions, you have to define configurations and define reductions on configurations. So it's not a reduction on processes.
But are you referring to this work by Bob Atke,
Okay,
given
before,
the
like,
notational semantics for CP?
Yeah, okay,
Is
but
that what you
also
have in
before
mind?
that, like Wadler's presentation, right? Or Lindley and Morris.
No, I mean for the PyCalculus you have a reduction semantics. You don't have configurations by themselves. So
Okay, but
so that's the part I don't get.
Okay, so I mean CP is a language for just a term language for linear logic, right? So and then you can put two processes next to each other, and then you want to have shared channels between two different processes which are not next to each other. And for that, I believe you have to define configurations, is how I understand it.
Okay. So this is so you're inferring that in order to have these unit configurations, because that's not
Yes.
part of the actual paper, right? So that's the part that was
Right.
confusing me.
Yes, and I mean, I think that there's a way around all this, which is like what HCP does, where you just add hyper environments and.
I think, I'm sorry, I think
Okay.
HPC, what it adds basically, it has a stronger correspondence to the PyCalculus, because
Okay,
in
yep.
CP, for example, you combine name restriction and process spawning.
Yeah, in the
So
typing
you
group.
could- Right, that's one thing. But HPC has restriction and parallel composition separates the two.
Yeah, which is what the
And
I think I wrote the mix
big
rule.
contribution, among other things.
Yeah, so it splits the normal cut into cut and mix.
Yes, exactly. So mix is just parallel composition, but you don't share a name yet, or you
Yes.
don't
Right.
share a channel yet. And they use hyper sequence in order to ensure that it's still deadlock free.
Yeah.
So, yeah, okay, I'm sorry to.
Yes, I mean, I don't know what is the best presentation of CP, which will have a typed reduction. And
I was actually wondering when you said that the problems, because I think CP actually, if I'm not mistaken, reductions do not preserve well. Oh, I'm sorry. Yeah, I think so that in CP you don't get under reductions. So the processes do not remain well typed.
right.
No, I mean they do. I mean on the transitions they're not well tied, but they're not supposed to preserve transition, right?
Well, I'm blanking right now, but there's the paper by Ornella and others at Concur, I think last year. So Ornella's not listening.
I'm not looking, but
Right, where you introduce the trees so that you remain well typed. The reductions mean, oh no, sorry, it's structural congruences.
That's what breaks.
Right, that's what breaks exactly in CP. Yeah, structural congruency is doesn't preserve well typedness. And I guess
I think there's a subtle point, because if you take the untyped structural congruence, of course, it's not preserved. The point is that there is a notion of structural congruence that can be recovered from the convenient conversions in the logic, right? So that's how it will come kind of automatically.
Yes. But in your work as well, you preserved it.
Yeah, because we were a bit more like detailed in doing that. Yes.
Right.
Yeah, sure.
Okay.
Sorry about that.
Okay, I'd be curious to know more about what it is. Yeah.
Okay, I just have one quick question. Yeah. So in your categorical semantics of this, you didn't talk about the exponential.
Yes.
Does that fit into this, into
Right,
the whole
so
picture?
adding exponentials to the CP syntax, I just know one presentation, but yes, it does fit into this framework, yeah. So the way you do it in a LNL model by adding another adjunction.
Yeah, in LNL I know how it works, but
Yes.
you were talking about the star autonomous categories and
Right,
this
right.
other stuff, and you didn't mention the
Okay, but
exponential.
I do know how to do it. I just don't know how to apply it to like an actual presentation of CP with exponentials.
Okay.
So in the semantics it does work, but I don't know about the syntax yet. That's it.
Okay, well, let's thank the speaker again.